All right, welcome everyone. My name is Søren Stobbe. I am an entrepreneur and physicist and associate professor at the Technical University of Denmark. It is my pleasure to welcome three panelists. Charlie Marcus, who is a former professor at Harvard, now professor at the Niels Bohr Institute and principal scientist or something like that at Microsoft's quantum activities in Copenhagen. Lillelund, who's the CTO of IBM Denmark, and Peter Krogstrup, who's a former professional musician, now turned scientific director, also at Microsoft. And I think we've just been hearing a lot of interesting things about the prospects of quantum computing and what it might do to our technology. I think what we will be focusing on for the next half an hour is trying to dig a little bit into it. What is a quantum computer? So let's try and be a little bit more nerdy. I don't think we should pretend to be able to give a comprehensive course in quantum physics and quantum information technology in half an hour. But I would like to try and sort of discuss this a little bit more. And I think actually the first question to ask, which I will direct to you, Charlie, is one main difference with quantum computers is that they're based on quantum bits as opposed to the classical bits. Could you say a few words about what a quantum bit is?
Sure. I want to start by saying I think that this is confusing to a general audience, and that first of all the sound is terrible. Does everybody agree?
It's a little bit terrible, yes.
It's only a little bit terrible. Maybe it's my microphone is not well placed. Is that better? I think that is better. Okay, let's see if that works. It's a confusing question because everything is quantum mechanics. The transistor operates on principles of quantum mechanics. The memory in your computer operates on principles of quantum mechanics. So the fact that there's this thing called quantum computing, you might want to ask, well, where's the boundary between a classical computer and a quantum computer? And I think that it's even fair to say that the ambiguity of that boundary has been exploited in the business world by people calling things qubits that may have no coherence and calling things quantum computers that may not operate on the same principles as quantum computing. The fact that there's no patented and licensed and accepted definition of a quantum computer is a market exploitable fact. So let me be specific. When you say what's the difference between a bit and a qubit, I think you can say that quantum mechanics has a very special property that does not fit our intuition of how the physical world works, and yet is the basis of the physical world that we live in, and that is that states don't have specific answers to measurable quantities until those quantities are measured. And I'm sorry to say that you can't give a better definition than that to a qubit by saying that when you call something, and you've all heard it 1,000 times, when you say it can be a 0 and 1 at the same time. I mean, we all just know how to parrot this answer and say it's a 0 and 1 at the same time. I think even our little blurb said it's a 0 and 1 at the same time. But what that really means is that it doesn't have a state until that state is measured. It is not used by any computer technology today. And it allows certain kinds of phenomena like interference, in which a state that can not be defined as a 0 and 1 can interfere in a wave-like way with another state, and it can also be exploited to make computers faster. So it's really taking advantage of the fundamental principle of quantum mechanics in a very general way, in a way that doesn't suit our intuition, but is with us and is an unarguable fact of life, and just using it in a computer technology scheme that has never been used before.
So, picking up on that, you mentioned the wave-like character of a qubit. That is certainly something that's very different from a conventional bit. That's also a concept that every researcher in quantum technology is constantly fighting. The serpent in the quantum paradise here, decoherence. Maybe, Peter, could you say a few words about what that is and what might be done to fight it? And why is it so bad? What is this?
Yeah, so these qubits is two-level systems, just like the bits we know from classical computing. The difference is that the two levels are in superposition. So like in a spin qubit, for example, you have the two levels are spin up and spin down, for example, or two levels in a quantum dot could be a qubit, and they are the same. They are these two states at the same time, and if you want to, they have the thing with quantum is that they interfere they're very fragile, so they very quickly interfere with other states around it, and if you are not able to separate the two levels from other things around it, then they will decohere. They will lose their two-level system coherence, and then you lose the information. So the big challenge actually in quantum computing, the development of quantum computing, is related to that fact that you need to create qubits that really doesn't see the world around it. That's very difficult.
No peeking.
And at the same time, that you could say the challenge is that you must be able to control these qubits, so you must be able to interact with them while they are not interacting with the environment. So this is indeed a difficult trade-off. So one company that has had made a number of interesting breakthroughs and also has actually delivered commercial products within quantum computing is IBM. And maybe you could say a little bit about your technology and also maybe tell a little bit about some of your relatively recent announcements of commercially available quantum computers.
So we are leveraging what has been done in semiconductors and have built on top of that. So we are, in fear of getting a little technical, we're using Josephson junctions at near 0 Kelvin temperatures to create our qubits. We have in 2016 we made the first quantum computers available on IBM Cloud with a software stack on top, which we gave access to everybody for free. We've been developing on top of that, and recently in January we announced the world's first commercially available quantum computer, which and I hesitate to use the number, but it's 20 qubits. But when we talk about qubits, it's also a little misleading, because there are good quality qubits and there are bad quality qubits, and there are a lot of parameters that influence the quality, and one of them is obviously coherence time, but also when you introduce interference, which is the way you operate the qubits, the quality of the interference is paramount to how well the quantum computer operates. So if you have an X gate, does it really flip the qubit 180 degrees or almost 180 degrees? We see parameters such as temperature variations in the microwave guides that we use for controlling the qubits, introduce error. So when we talk about commercially available 20 qubit computers, we also talk about quantum volume, which is, I think it's a little better measure of how well workloads can be performed.
So since we're discussing the status of technology, maybe you could also say a little bit about how you, since you have a commercially available product, how do you sell it? What's the organization?
Well, we don't really sell it because first of all, this is not a high volume production line we're talking about. We are using these in the cloud mainly because the physical setup that is required is difficult. We need to cool things down to 10 millikelvin to make it work. So you start out getting a lot of cooling going, and then you start adding a lot of electronics, and eventually you wind up with something you can use. And we've packaged all of that into a box, a 3 by 3 by 3 meter cube. But we're also developing on this. So we are making strides every month, every quarter, every year. So buying one now would not really make much sense since we are making most of it or all of it available through the IBM cloud. Unless you want to spend millions of dollars every year buying another one and another one, because this is a process that's going to keep on going. And Charles, you mentioned in the earlier session Moore's law, or will this be a complete new revolution? Actually, we do see in terms of quantum volume something like the Moore's law applying also to quantum computers, which I find is really exciting. Because in classical computing, Moore's law is breaking down. We're getting close to how small we can make things.
Yeah, I want to just emphasize that I realized about 2/3 of the way through my question in the last session that it was a kind of a stupid question, and I'd like to say why it was a stupid question. Because if you say, is it going to grow quickly or is it just Moore's law? Well, Moore's law is exponential growth. You really can't ask for much more out of a technology than exponential growth. And I think that because it would seem, I was casting Moore's law in the previous session as like the slow way. That was a mistake. I think that Moore's law is, we don't know whether technologically that was a one-off associated with CMOS and conventional computation, or whether we're going to be lucky again. But I think that we should recognize Moore's law would be just fine. And if there is a growth chart that looks like Moore's law happening now in this volume measurement or in any other kind of parameterization of improved quality, that's great.
I agree, but this is still early days. There are a lot of, as you well know, a lot of research obstacles that need to be dealt with, and not only just engineering problems, but the chart I saw from IBM Research, we have 3 dots, 16, 17, and 18. And trying to extrapolate on that may be a little bit dangerous, but the contours look like this might be a new Moore's law, even maybe a bit faster, as we see it doubling every 12 months rather than 18 months. But I will settle for 18 months if it turns out to be that.
Yeah. So I think let's go a little bit back to the more low-level technology. So you mentioned already you're using Josephson junctions. That means
Yes.
that you are working on superconducting
Yes.
circuits. There's actually a number of different contenders. So you could say that's maybe a little bit like conventional computer technology as it were back in the 50s, where there was a debate: is this going to be silicon? Is it going to be germanium? Is it going to be something else? The integrated circuit was not even implemented yet, so these were more like radio tube-like things, also in even earlier days. Microsoft has picked a rather different path, which may be more challenging. It may also eventually be a big win. Who knows? Charlie, could you maybe give us a little brush up?
Maybe I should let the quiet guy here take the.
I can say maybe then I will go one step back and say when we talk about qubits and we talk about the promising type of algorithms that quantum computing promises, they all build on the perception that we have logical qubits. And we are very far from
Yes.
having anything like that. And we don't even have good enough qubits to make error correction to make one logical qubit. The thing is, to come back to your question, is that I think we need a really advanced new type of technology that we haven't seen yet to make that big step to go to logical qubits. One idea that Microsoft is having and pursuing at the moment is topological protection, which is a fundamental property of some materials that's just been understood on the physical level at the moment, but it's super promising because they are protected from a lot of fault. We call it fault tolerance. It has a topological protection from the solder from outside, and it's a hard way to go because we don't. It's difficult to just make one qubit at the moment, but it has the promise. So that's one direction. There can also be other directions, or maybe we haven't found the silicon of quantum yet, and we have to be open for new ideas all the time.
Let me make one point about that, and it maybe nobody thinks this, and so it's a fake myth that I would be dispelling. But I'm gonna risk dispelling a myth that's a fake myth. The fake myth is that if this company has this many qubits, and this company has more qubits, and this company has fewer qubits, then the company with more qubits must have smarter, faster people working there, and that the company that doesn't. The truth is, all of these people that work at all of these companies, we all know each other. We all work together. The guys working in Yorktown Heights, were students of mine before they went there. So in terms of making qubits, we can all do the same thing. That's not the hard part. What's going on, and which I think is really interesting, is that even though these companies are nominally competing with each other, there's an effective dividing of the problem, because nobody really knows exactly the right way to do this. So the kind of choices that one company makes versus another company, whether topology is better than Josephson, whether spin qubits are better than, those are choices that have to do with vision and taste to a certain extent, and not about capability. I think technically speaking, we all have the same capabilities, but we're slicing up the problem in a different way. And you better believe that people at Microsoft who are working in topology are keeping their eye on people at IBM who are not, to see how that field is going, and that people at IBM are watching what happens in the topological sphere to see whether or not that all of a sudden starts rising up. And it really is a case of effective cooperation, even if that wasn't the intent. And it arises because simply most of the people working in this area know each other.
And it's a tough thing to solve.
And it's a tough thing to solve, and we better try to do it with a bit of cooperation, or else the big enemy is not being able to do it. It's not the big enemy is that somebody else is going to do it first. If some company makes an announcement, if IBM comes out and makes some announcement about something, how does Microsoft feel about that? The answer is, great, the field's moving forward. Things are happening. The field is alive. People are interested. The slopes are going up. It's a living, breathing problem. That's great news.
And there's so many components to it, and the field is so wide that, I believe that there's an infinite amount of work in the universe that needs to be done here. So the more we share in it, the better.
Right. I think that what you're seeing is effective cooperation. Whether it was intentional or not, at the end of the day, it's effective cooperation.
All right, so let's try and pick up a little bit on some of the questions ticking in. I think we have already more or less addressed the upper one, or at least indirectly. I think the short answer is it's too early to really judge. But I think it would be interesting to hear your input, Jan, on the third question. So the question is, how will private companies benefit from having a commercial quantum computer? You just said, well, they don't, because they may want to lease it instead. Okay, but then why would they want to lease it?
Well, to solve real-world problems. We're not really there yet, because the workloads that we can execute on quantum computers does not surpass what we can do on high-performance computers. So if you take the world's largest computer, IBM Summit, we're nowhere near that. We're not even scratching the surface. But if we can scale these computers, they promise to solve a class of mathematical problems that are intractable today. And that gives us the tools to do exciting things within chemistry. Give you a thought experiment. So rocketry started out in the 1920-ish with Werner von Braun playing around in his backyard, and in 1969 the United States put a man on the moon. And why did they do that? Because they developed a rocket fuel that had a high enough specific impulse to lift millions of kilos into space. How did they get there? By experimentation. So we have a span of 50 years where they were looking for something that reacted fast, but did not, to quote Elon Musk on this, result in rapid unscheduled disassembly. Well, if we can simulate these processes, we can cut down on the time finding the right compounds to get the job done. So, imagine if we have a quantum computer that is large enough to simulate the processes that goes on in a rocket engine. We would solve this problem within days, weeks, months, rather than 50 years. And that's, I think, the dream that all are pursuing. We're not there yet by any stretch of the imagination, but we see what Richard Feynman in 81 said, the world is quantum in nature, and in order for us to model that, we need quantum computation, and that's really what has been the big thing everybody's going for. Does that make sense?
It does, yeah. So, Peter, I would like to, we need to soon wrap up this session. Maybe it would be interesting to hear what is it actually that you're working on. So, where's the technology development level? So, what's the key? Maybe not, what are you going to do this afternoon? But seen over the past couple of months, what has been the biggest challenge in your everyday work?
So at Microsoft, we are pursuing this topological protection in materials, which we will use to make topological qubits out of, that are fault tolerant. And I'm more specifically involved in developing this material platform which will operate at millikelvin temperatures in fridges. And we know more or less what requirements from a theoretical basis, what is needed to build this platform, but engineering the platform is very complicated with the ways we are fabricating materials today. So we are developing both hardware, new type of fabrication hardware to build quantum technologies, which is also a whole development program in itself, and the way we then are finding ways to build, using this hardware to build the quantum hardware. And then there's the whole other pillar of measuring the properties and also understanding the fundamental physical properties of these materials. So we are able to make qubits in the conventional ways using these materials, but understanding the way to go forward with topological protection has been it's a complicated task, but we are learning every day.
Mm-hmm. So, all right, I think as a final question, which I will ask to the two gentlemen over there, I see it ticking in as a rather popular common question, which is, when will we see the first practical application where a quantum computer will be able to solve problems that a traditional computer cannot solve? Charlie, what's your bet?
I'm going to give a sneaky, tricky answer. You can give a serious, numerical answer. I'm going to wiggle out of that in the following way. The first quantum computers that we're going to see, which involve a few qubits put on the cloud, that involve solving problems that can be solved other ways more quickly, that involve solving problems that nobody cares about the answer, but which you can't solve using any known computer. Those are what everybody thinks of as being impractical. Those are in contradistinction to what the question's asking, which is, when will we see something useful? Well, I'm an experimental physicist. And what I want to say is that all of those preliminary steps are not only useful, they're essential. And that what we're going to see over the next 20 years is an ever-increasing sophistication such that last year's version will look terrible and next year's version will look impossible. And then the impossible thing's going to happen, and last year's version is going to look stupid, and next year's version is going to look impossible again. And anybody who's ever worked in an experimental laboratory feels that way every day. The thing you did last year is a warm-up exercise for bachelor students. The things that you have to do next year are impossible. And that happens, weirdly, year after year after year. And I think that to characterize the advance of this field in any other way, besides saying that every year, next year's problem will look impossible and last year's problem will look ridiculous, is to miss the point. The way technology advances is like that. It's not where one day, all of a sudden, something happens. That achieving the impossible thing year after year after year is what needs to happen and what will happen. Strange as it sounds.
Yeah.
There's my answer.
So, well, practical application. I think we need to, well, I see two roads being taken here. One is improving on the way we process using classical computers. But I'm also seeing a contour of a class of problems that are unsolvable on classical computers. Earlier this year, an article came out demonstrating a very obscure mathematical problem that can only be solved on quantum computers. So is it practical? No, probably not. But anyway, it confirms that quantum computers can do something that classical computers can't. And that may be the spark for something new. As to improvement on classical computers, I don't know. I could say 5 years, I could say 10 years, I could say whatever. I don't know. But if the development that we're currently looking at is any guide, and we do solve these impossible problems along the way, I think certainly within 10, 15 years we're going to see something that is going to surpass what we can do with HFC. That's my prediction, and you can beat me up for that later on.
Well, I'm happy that you were willing to do it.
All right, so we'll meet in 15 years for a fist fight. Thanks for everyone for attending, and thank you for the panel for joining.
Thank you so much, guys.